Hi, I'm going to introduce the paper of decoupling coarse kernels and operating systems. This paper presents a Barrelfish DC, an extension to Barrelfish OS, which decouples physical cores from a native OS kernel, and furthermore, the kernel itself from the rest of the OS and application states. In Barrelfish DC, a native kernel code on any core can be quickly replaced. Kernel state move between cores and the core added and removed from system transparently to applications and OS processes, which continue to execute it. And before going to introduce the whole paper, I would like to show a short outline of this presentation. First is about, I will introduce the motivation about trends in hardware and software. Then I will present about the implementation on booting and shutting down cores dynamically. And the rest of the paper about evaluation and the conclusion will be given by my partner. So we will see first what's happening to the hardware. Mostly today we are constrained by power consumption. This will build us, for example, reconfigurable cores, which means we can dynamically change behavior. So this is we already do today, like DVFS, which means dynamic voltage and frequency scheduling, and turbo boost and SMT. Also, there's some research technique such as core fusion, which allow us to fill cores multiple physical cores into simple, more powerful core, or split them up again. On the other hand, the future may have to do dark silicon, which means we can have many cores and we cannot power them all at the same time. So what that means for us, for adding and removing cores in the system? Well, we already do it today. For example, if cores fail or if relocated cores to different machines. On the other hand, you may take cores out of service because we will not power them all at the same time. Also, there's some there's heterogeneous cores in our machine, giving us asymmetric performance. And for example, one such logical conclusion of this would be conservation cores. Now we imagine that we build an OS in a dark silicon area. So you have set heterogeneous cores, and you need to switch between the cores based on your workload. But you also need to power down and take cores out of service because you don't have the power to put everything all at the same time. So this is the current OS model today that currently runs as a single program in all cores, and every cores run the same code. And it's hard to adapt like heterogeneous cores. So what happens if you move a core in such a system? Well, we have to go deep to the data structure to reflect this change. Typically, this requires global coordinations, and also the data structures may be globally shared, protected by locks. What happens if a processor holding a locks? So there's a lot of issues there. And what's happening to software? In software, we usually need to adapt to different workload in our OS. Now, general purpose kernel were very useful to adapt, but we still have to adapt to modify build, boot, and runtime. For example, to facilitate debugging with profiling and tracing, and sometimes application requirements are very strict, such as real-time support, and it's hard to adapt everything into general purpose kernels. Now, there are also research techniques that work by modifying or upgrading cores on the fly, as is case, for example, ksplice in Linux, or K42 in updates, or K42 upgrade mechanisms. So we argue that a good architecture model dealing with dynamic cores or adapting to heterogeneous cores or changing software requirements is multi-kernel model. In a multi-kernel, each core runs separate kernel program, and the state is currently in the per-core state into what we call OS node. Now we still have to run applications on the top of that, and the applications will share states between cores. Therefore, we replace the state between cores using asymmetric message passing. So, however, a multi-kernel model is not enough for dealing with dynamic cores, so we still need to deal with OS node. Therefore, we use as a basis with Barrelfish OS is an implementation of multi-kernel, and we add some features to the Barrelfish, and we call that Barrelfish DC, just as mentioned at the beginning. Treat cores as much as possible as plug diverse. So we will next about next of how we're booting a core dynamically with boots, drivers, and how we shut down a cores in systems. We use techniques that externalize kernel states that allow us to decouple cores, kernels, and operation systems. And I should mention that this paper focuses entirely on mechanisms and do not address the scheduling and policies for the kernel replacement, core power management, or application migration. Note that, also that this paper's main motivation in the Barrelfish DC is adapting the OS for performance and flexibility. So the author doesn't consider about fault tolerance and isolation for now. So first is about booting a new core. Bringing a new core online is a question about turning on, upgrading this table, and creating per-core state when needed. Previous version of Barrelfish also adopted this approach and boot all cores during system initialization, though there has been experimental work on dynamic booting of heterogeneous cores. Barrelfish DC targets a broader hardware landscape with complex machines comprising potentially heterogeneous cores. Furthermore, since Barrelfish DC runs a different kernel instance on each core, there's no reason why the same core should run everywhere. Thus, we need an OS representation of a core on machine which abstracts the hardware-dependent mechanisms for bringing the core up and down. Therefore, Barrelfish DC introduced the concept of a boot driver, which is a piece of the code running on the home core, which manages a target core, and it encapsulates the hardware functionally to boot, suspend, resume, and power down the later. Currently, boot driver run as a process but closely resemble a device driver and could equally run as software objects within another process. And we can see the process as follows. A new core is brought online as follows. First step is the new core is detected by some platform-specific mechanisms, and its appearance registered with the device management subsystem. And then Barrelfish DC select and starts an appropriate boot driver for a new core. The third step is Barrelfish DC selects a kernel binary and arguments for a new core, and directs the boot driver to boot the kernel on core. Next, the boot driver loads and relocates the kernel and executes the hardware protocol to start a new core. The last step is the new kernel initialize and use existing Barrelfish protocols to integrating into running OS. So booting a core in Barrelfish DC only involves two processes, the booting driver on the home core and the kernel on the target core. For this reason, we require no global locks or other synchronization in systems, and the performance of this operation is not impacted by the load on our cores. And we should think that the booting a new core is not the hard problem, because the shutting down a core is much harder, because we need to deal with the per kernel states, like we should take more space for scheduler queues and memory pools and page tables. As a result, we need more time and more energy. However, we want to remove the core as fast as possible. The general approach, like Chamberlain's, they followed get state out of the way quickly and dismantle it later or lazily. So how does it work in our OS, in the Barrelfish OS, Barrelfish DC OS? First, close them away, and we are able to capture this OS over all per core states, and we move it to a different core. Now, we add an OS node scheduler into kernel that is able to dispatch the different OS nodes. And we call this case that one OS node removed to a kernel that already have one OS node temporarily parking OS node. And we can already notice here that this approach is highly scalable, because we only involve the two cores in process right now. We don't need to normally coordinate in these systems. So what happens next? We can either move back to the previous course or move somewhere else. So what is OS node? And how do we capture this OS node? This is typically not clear in OS. Per core state is not explicitly defined and typically have many different data structures. So in this paper, they use the partition capability system to exploiting capture OS nodes, meaning entire per core states in a single data structure. I want to explain first about the frame and C code shown in the picture. Capabilities are typed to reflect what the memory is used for. A frame capability refers to memories that the holder can map into their address space. A C code capability refers to memory that is used to store the bits representation of capabilities themselves. This captures all access information and memory allocation about applications. So all per core states in kernel are now be accessed to the structures or reconstructed from the capability tree. We still need to be able to reach this structure and pass it around in our system. Therefore, we add KCB, or kernel control block. KCB combines some states that don't need to persist across a kernel start. Also, KCB is the capabilities itself, means we now have representable handle in system to move entire per core state or out. So this method of state externalization and the dynamic core booting is much more general mechanisms, because we are now able to move per core state around and inherently in our systems, and we can also replace the kernel dynamically on needs. Express needs our OS nodes. Also, I want to talk about something about how to deal with the interrupts. In general, it is distinguished to three types of interrupting in systems. First, handle local to cores and CPU driver like timers. And the second one is inter-processor interrupts, which send between OS nodes, and also the device interrupts. So what happens if we have a device that ran on some cores and is migrated to a different core? Right now, we essentially masked all interrupts on the core, and then we have registered the interrupts on the device driver. So we typically doing this process is sometimes happen between, and you have to go and check again. If something happened into device, or you can pull the device while doing this shift. As a part of evaluations sections, we are going to see how exactly do this and how fast it is. So welcome my partner.